Okay, so let me all right. So let us quickly. I think this is fine. Yes, let us quickly recapitulate what we did. Okay, so we talked about relations. If you have a set A and any relation is a subset, let's talk about binary relation on A itself. It's on subset A, and then we had a notion of equivalence relation, which is reflexive, symmetric, and transitive. Okay, so one implication of this is that suppose X is an element of A, and let me denote this box X as the set of all Y such that X is related to Y. Let's denote this by this, and if you take another Y and consider box Y, in the case if R is an equivalence relation, you all know what we have is that if box X, so X box X is the set of all Y's, or rather set of all Z you can say, which is related to X by R. Similarly, box Y, if X intersection box Y is not equal null, then box X equals box Y. All right. So what this means is that what this means. Anyway, so I hope your screen is visible. So what this means is that any relation, any equivalence relation induces a partition. Induces a partition, meaning that first let us see what is a partition. A partition is let me no, don't need this. Yes, I hope I have a better screen. Yes. A partition of a set A is a collection of subsets of A, and let's call them A1, A2 up to AN, such that you take the union over all I, AI, you get back A. This means they are exhaustive. And intersection of AI and AJ for all IJ is equals null. Okay, so basically, as we discussed in the last class, so these are non-overlapping subsets. So you can easily prove that any equivalence relation induces a partition. Any equivalence relation induces a partition. I think I'm not going to the complete proof. What it basically has, suppose I have two sets, AI and AJ, let's say they do not, let us first prove the exclusivity. Let us say there is an element X which belongs to both of them. That means the intersection is not null. Then for the case of equivalence relation, you can prove that if this is related to this, and then by and this is also related to this because they are the same element, by transitivity, this will also be related to this. So you can show that for every element of AJ also belongs to AI. So they are basically the same subsets. You can easily put. Let's take some example actually that will make clear. So let's consider one particular equivalence relation called the congruent modulo relation. Okay, say R, I consider as the congruent modulo relation over Z, set of all integers. So this is 1, 2, 3, the set of all integers. Okay, so two integers A and B will be related if we denote by this symbol. A is congruent to B modulo n, where n is another integer, n is another element of Z. A is congruent to B modulo n. What it means is that the remainder upon dividing A by n and B by n are the same. Okay, say let's take an example. Say 7 is congruent to 13 modulo 3. So if I divide 7 by 3, you get a remainder of 1. If you divide 13 by 3, you get a remainder of 1. So 7 is congruent 13 modulo 3. Okay, so basically this is given an integer n, you can define congruence. I think all of you know this. There is another way of saying this, that if A is congruent B modulo n, then A minus B is perfectly divisible by n. A minus B is perfectly divisible by n. So this congruence relation induces a partition. No. No. Anyway, I'm using whiteboard for the first time. Okay. Okay, so this is your Z. This is not the symbol that is used. Okay, so you have minus 1, minus 2, 0. 0 is not there. 1, 2, and so on. Okay, so you see, if you form partitions which are say you consider congruence modulo n, where n is something. Okay, can anybody tell how many subsets will be there in the partition of Z? How many subsets will be there if we consider the you can easily show that this is an equivalence relation, because A is of course related to itself because A minus B is 0. And if A is related to B, B is related to A, because if A minus B is divisible by n, B minus A is also divisible by n. If A is related to B and B is related to C, then A is also related to C. So this is indeed a equivalence relation. So can you tell me how many partitions will be there? How many elements will be there in the partition? How many subsets will be there in the partition? Any idea? So you consider Z to be the let's say you can take Z plus, only positive integers.
There are n partitions.
N partitions? Correct. So what will be these partitions exactly? Can you tell, elaborate little bit what these partitions are?
They are the remainders.
They are the remainders, exactly. So you have remainders from 0 to n minus 1. You have n possible remainders. so the numbers, these integers will be grouped. Each group will be of infinite size, as you can imagine. Each group will be of infinite. Each subset will be having infinite, rather LF0 cardinality, and then each group are the set of integers which, upon dividing by n, have the same remainder. Right? So many partitions will be formed. You can easily check that each of these subsets, that all the numbers which are having the same remainder upon dividing by n, they are exhaustive, because if you can easily form a mapping. You pick up any number from Z plus, it has to belong to one of these categories, one of these groups, one of these subsets. It has to belong to. So it is exhaustive. You can also prove to be exclusive, there to be exclusive, because if you divide a number, the remainder is fixed, is only one number, and then so hence it has to belong to only one of these partitions. Okay, so this is an example. This way there are several examples possible. So the reason I talked about all this is just to drive it in your mind that it's very important thing. Every equivalence relation induces a partition, and every partition can be used to define an equivalence relation. Every partition can be used to define an equivalence relation. Let me check it there. Okay, is there some problem with the display? Oh, okay, I messed up. Forget it. Let me stop the thing. Let me go to my slides. Okay, maybe I'll come back when I have to explain something. Let me quickly come back to what we're discussing now. And now is it clear? Now everybody can see the slides properly. Anybody,
Yes,
please reply. Yes, thank you. Okay, so so now if we replace, you have your reflexivity and transitivity, you replace the symmetric by antisymmetric. What it means is that for any two elements x, y in A, if x is related to y as well as y is related to x, implies x and y are the same. So instead of a symmetric, you have the antisymmetric. And then relations which are reflexive, transitive, and antisymmetric would be called as partial orders. You can think of themselves. A typical example of a partial order is the less than equal to relation over numbers. Any numbers, the less than equal to relation. It's a typical example. Often it helps you visualize things. Okay, and connect. Just one more small definition, which we'll use somewhat later. If two elements x and y, there is an partial order often represented by this less than equal to, this specialized less than equal to symbol. Often you don't use r to represent that it is a partial order. We use this less than equal to symbol. Often two elements x and y would be called comparable with respect to a partial order if either x is related to y, as this let me say x is less than equal to y, or y is less than equal to x. Then I would call x and y to be comparable. All right. So a connected relation is one where every pair of elements are comparable. Every pair of elements are comparable. And if you have a partial order which is also a connected, where every pair of elements are connected, then we call it a total order. And we also saw that we can represent partial orders using something called an Hasse diagram, where every node is an element of the set A, and there is an undirected edge between two nodes. If this undirected edge they are the minimum set of edges. Other edges also exist, but they are transitive edges that can be inferred from these undirected edges. And We drop the self edges, the reflexive edges, because we know they are anyway there. And since we don't have symmetric property, the back edges are not there. So we can adopt a convention that all edges go up. All edges go up. So if we adopt this convention of an Hasse diagram, we can see that any total order will look like a chain. A partial order might not look like a chain. It may comprise of multiple chains which are connected. Now let us look at another kind of relation, that is which is a slightly more restricted version of a partial order relation. We call a relation to be a strict order if it is irreflexive, meaning x is not related to itself. For all x is not related to itself. And asymmetric, there is another condition. If x is related to y cannot be related to x. So a strict order, a typical example of a strict order is the strictly less than, not less than equal to, strictly less than relation over numbers. Okay, so in fact, asymmetric property you can prove by just irreflexive and transitive. So a strict order is one which is irreflexive transitive, meaning it is also asymmetric. The thing is that we also mentioned that you can convert a strict order to a partial order and vice versa, just including or excluding the equal to x equal to y, this operation with the definition of the relation, definition of the less than equal to relation. So if you exclude the equal to y, that means you include x not equal to y, then a partial order becomes a strict order. And if you include the x equal to y, then a strict order becomes a partial order. So you just need to add or remove the equality condition in the relation. That converts a partial order into strict order. So there is a kind of duality between them. You include the equal to or remove the equality to get one back from the other. All right. So the moment. All right, a set A along with this partial order relation, let me call it less than equal to, is called a poset. It's called a poset. You take any subset of a poset, there are two elements which are important. You take any subset of a poset, there are two elements that are important. One is called the maximal element, or one other is called the minimal element. Okay, so the maximal element is this way. So you take any subset. Let's take the right diagram in the picture. Let's take the right diagram, and this is a poset. These are all divisors of 36, and then there is an upward edge if the lower number divides the upper number. Say 1 is related to 2 and 3, 2 is related to 6. Note that here there are many transitive implied edges too. For example, 1 definitely divides 12, 18, 36, everybody, but I have not drawn those edges because they are redundant. They can be inferred from this. So this is a poset. Let's look at a subset of the poset. Let's look at the subset 12, 18, 6, 2, and 3. The middle, this 4 kind of thing, 12, 18, 6, 2, and 3. Let's consider this subset. Let's consider this denote it as the subset S. So an element capital M belonging to S would be called a maximal element if there is no element in this subset which is greater than this maximal element. There is no element in this subset which is greater than this maximal element. Okay, so 6, is it a maximal element? No, because there are two elements, 12 and 18, which is greater than 6. It is not a maximal element. 2 definitely not. There is 6 and 12 and 18 which are greater than this. 3 not. So what are the maximal elements here in this subset? Silly question. What are the maximal elements? Just to see you are listening. Okay, so 12 and 18. Okay, I'll not see that you are listening or not. So 12 and 18. You see, if you consider the set 12, 18, 6, 2, and 3. Then the elements 12 and 18 there is nobody in this set which is greater than either 12 or 18. So these two are the maximal element. Similarly, what are the minimal elements? 2 and 3 are the minimal elements. Note one thing that it is obvious from this is that there can be multiple maximal and multiple minimal elements of a subset. Okay, is that obvious? You can think of it a little bit. It's not really obvious. There can be multiple maximal and multiple minimal element. Now, let us change the definition a little bit. Okay, and let us, instead of saying that there is no other element in S which is greater than this, let us change the definition a little bit and say that all other elements of S are less than this, less than equal to this, sorry. All other elements of S are less than equal to this. Okay, and vice versa. That means all, if we talk about the minimum element, all other elements, not all other, all elements of S are greater than equal to this. All elements of S are greater than equal to this for the minimum, and for the maximum, all elements of S are less than equal to this. So can you tell what are the maximum elements of this subset 12, 18, 6, 2, and 3? Can anybody tell what are the maximum elements? Am I audible?
Sir, there is no maximum element for this subset.
Exactly. Why?
So because either of 12 or 18.
Okay, what is the
less.
either of 12 and 18? Yes.
So they are not less greater than equal to all the other elements. Like for example, 12 is not greater than equal to 18. Similarly, 18 is not greater than equal to 12.
Exactly. So there are no max. So it is possible that there is no maximum element. It is possible that there is no maximum element. But it can always have a minimal element. It can always have a maximal or a minimal element. It is possible that it does not have a maximum or a minimum. If so, in this case, you have seen that there are multiple maximal element and multiple minimal element. 12 and 18 are the maximal element, 2 and 3 are the minimal element. If in a set there is a single maximal element and a single minimal element, they are called the greatest element and the least element. If it turns out that there is only, for example, if I consider the entire poset, if I consider the entire poset, you see there is only one maximal element and only one minimal element. Only one maximum and only one minimal element. So this maximal and minimal element would be called a greatest and the least element. So 36 is the greatest element of this poset and 1 is the least element of this poset. Similarly, in the left hand side poset, is the greatest element and null is the least element. So if a poset has a single maximal element or a single minimal element, they are called the greatest and least. It is possible that it can have a greatest element but not the least element. That's also possible. It is possible that it does not have either a greatest element or a least element. But it will always have a maximal element. It may not have a maximum element. Now let us do one more thing. Let us consider a single element of this set. Let us consider 6. Okay, let us consider 6. The other element, the collection of the set of other elements which are greater than equal to 6 are called the greater elements of 6. Or sorry, not the greater, they are called the upper bound of 6. You take all the other elements which are greater than equal to 6. So what is the upper bound of 6 in the right hand side diagram? What is the upper bound of 6?
12, 18, 36.
12, 18, 36. And similarly, you can define the lower bound of 6, that is the collection of elements which are less than equal to 6. So 2, 3, 1 are the lower bound of 6. Note that 4 and 9 do not belong to the lower bound of 6. 4 and 9 do not belong to the lower. 2, 3, and 1 belong to the lower bound of 6. Okay. Now let us look at one more thing. So let's consider the upper bound. I am not discussing the lower bound. Similar things will apply to the lower bound. Let's consider only the upper bound. So the upper bound is 12, 36, 18. This is the upper bound of 6. You take that member of the upper bound which is not which is less than equal to all other members of the upper bound. You take that member of the upper bound which is let me rephrase it a little bit, which is not greater than equal to, let's say, the other members of the upper bound. So which is that element in this upper bound which is not greater than equal to? Which is not greater than equal, or rather I can also put it this way, which is less than equal to all other elements of the upper bound. So among this set 12, 18, 36, find out one of these three which is less than equal to all other elements. Can anybody say? Does it exist?
So it does not exist.
It does not exist. So let's take another example. Let's take 4. Okay. So what is the upper bound set of 4? What is the upper bound set of 4? Yeah, speak up. What is the upper bound?
1236.
1236. And what is the lowest upper bound? Now I define the term lowest upper bound. It means that the member of the upper bound which is less than equal to all other members of the upper bound. So among 12 and 36, which is the lowest upper bound?
12.
12. So here the lowest upper bound exists. So for 4, the lowest upper bound exists. For 6, the lowest upper bound does not exist. So if you pick up a single element, you can either have a lowest upper bound or need not have it. Similarly, the same thing, you can have a greatest lower bound. For example, 6 you see does not have a greatest lower bound, whereas 4 has a greatest lower bound. The greatest lower bound of 4 is 2. Okay, so for single elements, we can have the greatest lower bound and the least upper bound. Sometimes, not always, sometimes. All right, so we have seen two concepts. One is for a single element of the poset, we can have a greatest lower bound and the lowest upper bound. And for a subset of the poset, you can have a maximal element or a minimal element, multiple. And you can also have a maximum or a minimum element. You can have a greatest element or a least element. Okay, so these things we have now defined. Now, let us consider any. So this definition holds for any subset of the poset. Now, let us consider subsets which consist of only 2 elements of the poset. Only just 2 elements of the poset. So let's take at any 2 elements. Let's take 4 and 6. Let's take 4 and 6. So this is a subset. This subset 4 and 6. What is the what is the maximal element of 4 and 6? You just consider the subset 4 and 6. What is the maximal element? Anybody? What is the definition of maximal element?
4 and 6.
4 and 6, what is the maximal element? 4 and 6, does it exist? Or both of them? Yeah, in this case, it is both of them. Okay, so so since there are two, you do not have a greatest element. Oh, it closes after 1 hour. Wait, so CRM tries to program everything. Yes, his Acrobat closes after 1 hour. Okay. Okay, so now, okay, anyway, let us move to the next slide. So now let me give you two definitions. So you take any two element, X and Y in the poset. I call a third element, which I call the meet of X and Y, denoted by this symbol. So you take any two element in the poset X and Y, and consider a third element, which I call the meet of X and Y, denoted by this symbol X upper hat Y, upper pointed hat Y. Okay, so it is the maximum of all lower bounds of X and Y. So you take the lower bound of X, you take the lower bound of Y, and your X hat Y, let's say, or the meet of XY is nothing but the maximum. Let's call it W. So W over the entire poset, such that W belongs to the upper bound of X and W also belongs to the upper bound of Y. So sometimes this would be called the greatest, sorry, not the upper bound, this would be the lower bound. X is greater than W, Y is greater than W. So this would be so this is the greatest. So this is the maximum over the lower bound of X and lower bound of Y. That is called the greatest lower bound or the meet. Greatest lower bound or the meet. Sometimes also called the product of X and Y. So let's take this example. So you tell me what is the meet of 12 and 18? What is the meet of 12 and 18 in the right hand side diagram? What is the lower bound of 12 and of 12? What is the lower bound of 12? Anybody? What is the lower bound of 12? Hello?
1, 2, 3, 4, 6.
Yeah. What is the lower bound of 18?
1,
1,
2, 3,
2,
6, 9.
six, 9.
What is the common lower bound of 12 and 18?
1, 2, 3, 6.
Right. What is the maximum common lower bound of 12 and 16?
6.
Yes. So 6 would be called a meet of 12 and 18. 6 would be called a meet of 12 and 18. Okay, 6 would be called a meet of 12 and 18. Okay, and now look at the other way. So let's look at 2 and 3. Any two elements, 2 and 3, let's look at. So what is the common upper bound of 2 and 3? What is the common upper bound of 2 and 3?
6, 12, 18, 36.
Yes. What is the lowest common upper bound of 12 and 3? 6.
6.
So 6 would be called the join of X and Y. 6 would be called the join of X and Y. Okay, so this join and meet can be thought of as binary operators. They can be thought of as binary. It takes the operator take two elements of X and X and Y of A and produces a third element. The first one, the third element, we call the meet of X and Y, and the second one, the third element, we call the join of X and Y. Okay, and how do you find meet and join? You take all other elements of the poset beside X and Y, which are the let's say take the case of join, which are greater than which belong to the upper bound of x, the common upper bound of x and y, and take the smallest among them. That is the join. Similarly, take the common lower bound of x and y, take the maximum among them. That is the meet. Okay, that is the meet. So let me okay, let me just complete this definition and then I'll pictorially explain what it means. All right. So a partially ordered set, a poset, is called a lattice if every pair of element have both meet and join. If every pair of element has both meet and join, it would be called a lattice. Then that poset would be called a lattice. Okay, so let me quickly draw some diagrams. I think this is better. Okay, so if this is your x and this is your y, and there is a structure like this, and there is a structure like this, this will be your join, and this will be your meet. Right? Is that clear? All right. Now answer this question. If this is your x and this is your y, or this is your y and this is your x, and there is an edge like this. In the first case, what is join xy? Can anybody tell what is join xy?
X.
X itself. This is your join. And this is your meet. Similarly, here this will be your join and this will be your meet. What is join xy and meet xy in this case? In this case, so I have a chain. I have a chain joining x, and they are not immediately joined, so immediately connected, but there is they belong to the same chain. They are parts of the same chain. So what is join xy and what is meet xy? Anybody? Note that there are transitive relations. I've just drawn the Hasse diagram. Anybody? What is join xy and what is meet xy?
Still, there will be x and y only.
They will be
Yes,
x and
sir,
y
X and
only.
Y.
So exactly. So what I'm trying to say that even if they are in a chain, so there are only two patterns of finding join and meet. If they're in a chain, either a single chain or a long chain, the join and the meet are nothing but the two ends of the chain. Two ends of the chain. And if you have a diamond-like structure like this, if you have a diamond-like structure like this, then the join is the top of the diamond and the meet is the bottom of the diamond. Okay, so these two structures are common. There may be other, I mean, there may be more complicated thing, but in these two, it is clear what is join and what is meet. This will help us. So now next what we want to do is that given a Hasse diagram, we want to check whether it is a lattice or not. That is the next job we'll do. I'll show you some Hasse diagrams and you have to tell me. Note that in order and partial order set to be a poset to be a lattice, every pair of element has to have a join and meet. Every pair of element. And one more thing you see, because of the property of this maximum and minimum, if the join and meet exist, it will be unique. If you take two X and Y, they can have only one join and only one meet. They are unambiguous, they are unique. Okay, the question is whether they exist for every pair or not. Let's take some example. So I have drawn a number of posets. First case, is it a lattice? No, I have not numbered, labeled the nodes, but I can label them as I go along. Okay, the first case to the left, the chain to the left, is that a lattice? You take any
Yes.
pair of elements, like the top and bottom, middle and bottom, it's a poset. It always has a join and a meet. The second one, the diamond, is it a lattice?
Yes, sir.
Okay, so what is the join of the top and the bottom element? What is the join of them? You see, they belong to the same chain. So either you take this chain or you take this chain. The top and the bottom are part of a chain. So they are join and meet at the top and bottom themselves. And these two form a diamond structure. Okay, what about the third one? What about the third one? Is it a lattice?
Yes, sir.
Yes, there are no elements which does not have a join, and this is also like. In fact, I like to tell you that. Let me tell you this box kind of structure. No, this diamond I said before, but you can think of it as a square also. This is a very common pattern. This is how the name lattice first came into picture. So this is. This is a two-dimensional structure. Sometimes you can have a three-dimensional structure like that also. Is this a lattice? You see, this is like a cube. This is like the corners of a cube. I have drawn very poorly, but if you are imaginative enough, you can see a cube in it. Is it a lattice?
Yes.
It is a lattice.
Yes.
You take any pair of elements, you have a join and a meet. This is actually called a cube. If you go to higher dimension, you get a hypercube. These are a common lattice structure. That's why the name lattice. So this looks like a crystal structure, and they were called lattices. And in fact, the physicists use this a lot. These kind of structures. Okay. Anyway. All right. So now let's come to this, the fourth one from the right. So 1, 2, 3, 4. This one. Is this a lattice? Is this a lattice? Is this a lattice? Can you find the way to prove that it is not a lattice? Is to you have to identify two elements which do not have either a join or a meet. So are there two elements which do not have a join or a meet? Just think a bit. Are there two elements which do not have a join or a meet? Note that, okay, one thing I should warn you against is that I am just speaking in terms of looking at the geometry and doing it, but the real mathematical way to do this is to apply these definitions. Okay, you have to actually check for this condition. But okay, in this case, maybe you can, these are equivalent. These are easy cases, so you can visualize them this way. Okay, so is this the fourth one? Is this a lattice? Any answer? Can you find a pair of
Yes,
nodes?
sir. It's a lattice.
It's a lattice. So what is
Yes,
the
sir.
what is the meat of this and this? What is the meat of this and this? Because see, let me tell you, see, if there are two nodes which belong to a single chain, then we need not bother because they are all comparable to each other. Only reason, only time when we are the pairs we should look at when the elements of the pair, elements forming the pair are not comparable. Okay, if they are not in a chain, we did not bother. Everything is comparable. So when things are comparable, the top one is the join and the bottom one is the meet. Top one is the join, bottom one. So don't bother about them. But only you should critically look at the non-comparable elements. So these two are non-comparable elements here. These two are non-comparable elements. This one does have a join. These two non-comparable elements does have a join. These two have a meet. But the question is, does these two have a meet? Now apply the definition and think. Does these two have a meet? So what is the lower bound of, I hope you can see the cursor. What is the lower bound of this element? What is the lower bound of this element? This and this things which are there in the same chain. What is the lower bound of this and this? Is this and this. So what is the common element between these two? This. Is this common element the maximum? Is this common element the
No.
maximum? It's the single element, so that is the maximum. So this is also a lattice. What about this? What about this? So I have drawn a kind of diagonal here. Now you tell me. So now, if we look at the lower bound of this left top, this thing, and the lower bound of this, so the lower bound of this is this and this, the lower bound of this is this and this. So the common elements of the lower bound and these and this. Okay, so what is the meat of them? What is the meat of them? This one. Similarly, you look at these two elements. What are the upper bound? The upper bound of this left, this is this and this. The upper bound of this is this and this. So the common upper bound is this and this. Okay. So what is the minimum among them? This. So this is the meet. So this is also a lattice, right? So can you check for all this? So it's important that you check for all this. In fact, we will give you some assignments where we give you some Hasse diagrams and you have to check their lattices or not. So the trick is you have to check for every pair of elements. But the hint is that the pair of elements which lie along a chain, don't bother about them. Only consider the pair of elements which are not comparable, which do not lie along a single chain. And see they have a meet or a join, meet and a join rather. Okay, so I'll circulate these slides. You please try out on this. It's important for it's easy. It's child's play. So you have to just try out on this. Okay, so now if we look at this meet and join, I don't know I have time today or not. If we look at this meet and join as binary operators, and then there are some properties that they satisfy. There are some properties that they satisfy. I'll just talk about this property. Maybe other properties I have to talk in the next class. So these are called the order properties, which basically means that if we take two elements x and y, they are lower bounded by their meet and upper bounded by their join. They are lower bounded by their meet and upper bounded by their join. So x and y lies between the meet and the join. Lower bounded, upper bounded means again this less than equal to symbol. Okay, and I said before that if x and y are comparable and x is less than equal to y, then the meet of x and y is x itself. So and similarly the join of x and y is y itself if it is x is less than equal to y. So in fact this can be used in the other way around also. If we know again there is a duality. If we know a meet of an element with another element is the element itself, then the first element is less than the second element. If meet of x and y is x itself, then x is less than equal to y. Similarly, if the join of x and y is y itself, then x is less than equal to y. Basically, earlier I said this, then I said this, then if I know this, I can also say this. So it is if and only if. There is a kind of property that if x is less than y, if x is less than equal to y, if we take the meet of x with any element z, and if you take the join of x with any element z, and if you take the join of y with any element z, the join of x with z will be less than equal to join of y with z, and similarly for the meet also. Okay, similarly of the meet also. Then if this is a transitivity kind of thing, if x is less than equal y and z is less than equal to w, not transitivity, it's kind of combination. So the join of x and z is less than equal to join of y and w, and similarly the meet of x and z is less than equal to the meet of y and w. So these are some basic order properties. Let's try to prove one of them. Let's try to prove this. So this says that if x is less than equal to y, then if you take any other z, the join of x and z is less than equal to the join of y and z, and similarly for meet. Okay, so it's easy to prove that let v be this meet and u be this join, and by transitivity v is a lower bound for y and z, and since this is the maximum lower bound, so v will be less than equal to u. So you look at this diagram, you can prove this. So these are some basic properties. We'll see other properties also later, and they are really important about this join and meet, because this join and meet we'll see they will show them to be equivalent to logic gates. You can already maybe figure that out. They are equivalent to the AND and OR gates. So the logic gates that we talked about are nothing but some kind of maximum and minimum operation on the partial order sets, and that will later give us the algebra and other things. Okay, so let me stop here. Let me stop here.